So in this video, we're going to do the last of our NoSQL exercises, and these exercises come due Wednesday the 15th, and this is the final of the NoSQL lectures as well. But before, and let me kind of show you what the end result is. What we're going to do in this exercise, we're going to use the recursion that we talked about a little bit in the last lecture. And we're going to use that to display bill of materials and also to generate some JSON data that can be incorporated in a visualization. And I'll show you the visualization if I go to the module here. And in the NoSQL modules, you'll notice down here toward the bottom, there's tree.html. And I'm going to pull that up. This is an HTML file, and within it, it has some JSON data, and it's making use of a JavaScript library called D3. I've talked about D3 before, and I've done in my story analyzer, several of my visualizations are D3 visualizations. And basically, here you see the bill of materials for one of the bikes. So ultimately, we're going to be generating the data that produces this. And in order to do that, we're going to use recursion, because what do we get here? We have a tree. And as I showed you before in the lecture last time, recursion is a big thing when it comes to trees. I think I would like to, before we start the exercise itself, though, to kind of review a few things and talk about a few things having to do with these examples that I showed you last time with recursion. So one of them was the factorial, and the factorial was a very simple example in the sense that you can you're basically it's just calling itself once. So here we have the function, which is calling itself. And remember, there's always a stopping condition and as well as a recurse condition. So you have to decide when to stop at some point. So this was just calling itself, and as I had shown you, it could easily have been done in a loop, because basically you're just making a list here. If you can see the stack here as it's growing, it's just kind of just going up and then coming down. So that could have easily been done in a loop. We didn't really need recursion for something like that. But when you came to something like the Fibonacci number, where it's calling itself twice, this is not as easy to do without recursion. It can be done without recursion, but in order to do it, you actually have to have a stack data structure, make use of a stack data structure. And well, it so happens that the call stack, the underlying programming environment has the call stack, and so with recursion we're taking advantage of that call stack. But you could be doing Fibonacci or any of a number of other things that we do more easily with recursion, non-recursively, but we have to make use of a stack. So notice what happened with the Fibonacci number was it wasn't just kind of this list being generated, but essentially it's a tree. It's a tree data structure. And the tree data structure is something where you have a node, and the node has children, and those nodes might have children, etc. And each child is a child of exactly one node. It's not like, so that's a tree data structure. A node can have many children. A child will have exactly one parent node, or maybe none. Okay. And so what was happening with the Fibonacci numbers is we were traversing basically depth first as a function was being called. So let me go back up to this. So this function would be called, and then it would get into its point of calling itself the first time, and it would get into then the next one to get into its point of calling itself the first time. And so that would have been this depth first traversal. Notice what it wasn't a breadth first traversal. In other words, we didn't start here and then go to each of these two nodes at this level, and then go to each of these four nodes at this level, and then go to each of these nodes at that level. No, it's depth first. You're completing the search in exactly that same sequence. So that was an example of of recursion. And then there was the towers of Hanoi, which also was calling itself twice. So in both of those cases, your tree that was being generated could be thought of as a binary tree. That means the number of branches coming out is 2 because the function is calling itself twice. You'll also notice that as you go further and further, deeper and deeper into the tree, and if we haven't stopped, then we're basically doubling the amount of nodes um, at each level. So that same sort of thing was taking place with Fibonacci, as well as with the towers of Hanoi. And then my final example was this one, where I'm saying, okay, let's just be arbitrary in terms of our number of branches and our depth level that we want. And it basically was showing, again, illustrating the fact that this is, in fact, a depth-first traversal of the tree. This is the sequence in which nodes have been created in this depth-first fashion. And you can experiment with that. Now, point being here, that you can have a tree, in principle, that goes as deep as you wish, and that branches, as many branches coming off of a node as you wish. And look at what happens in this scenario right here with the Fibonacci numbers. With the Fibonacci numbers, as the number gets bigger and bigger, so the Fibonacci this was a Fibonacci of 4, and this is how many nodes we wound up with a Fibonacci of 4. You have a Fibonacci of 5, kind of double that, Fibonacci of 6, double that, Fibonacci of 7, double that. And you can see that we start to have an exponential growth, and that it takes more and more time to tackle something like this. Let me show you this. I'm going to pull up idle. And let me go to the Fibonacci code. Here's the Fibonacci function. And I'll go ahead and paste it into the shell. So now we have this function. And if I say Fibonacci of, say, 10, it gives me a response pretty quickly. Say I said Fibonacci of 20. Still pretty quick. Let's try Fibonacci of 30. It took a little bit longer. Let me go to Fibonacci. I'm not even going to go to 40 yet. I'm going to go to, say, Fibonacci 32. Can you see it's taking a little bit more of a lag? Fibonacci 34. It's taking quite a lag that time. If I was to put in Fibonacci 100, I'm sure that we would be killing the shell way before that got done. So this points to the problem that is often encountered in AI, and you'll have when you're generating trees. And if I mean, the Fibonacci of 34 took that long to calculate, Fibonacci of 100, you're not going to get the result of that. Now, this is an algorithm, but it's an intractable algorithm. The intractable is actually a technical term. It's not the same as uncomputable. I talked about uncomputable when I was talking about self-referential kinds of stuff, and this whole mystery with Gödel and Escher and Bach and all that kind of stuff. It's not that it's uncomputable. It can be computed. There is an algorithm that can do it, but the algorithm will take so long on a large search space that it's just never going to get the job done. And AI often faces those problems. Let me go back to the tree here. So this is a simple tree where you've got 2 different choices coming off of each node. Let's compare this to a chess game. So in a chess game, consider each node to be a board position. And from a board position, how many moves can you make? Well, you can make lots and lots of moves from a given board position. Now, many of those moves will be stupid moves, but they'd be legal moves that you can make. And so that leads you to another board position. And out of that comes lots and lots of moves that could be made. And that leads you to another board position. And of course, what you're trying to get to down at the very bottom here is the position where you have put your opponent into checkmate. And how are you going to get there? Well, if we're just going to do a brute strength, searching this entire tree 10, 15, 20, 100 moves in advance, that's an example of an intractable problem. It would not be doable. And so in AI, oftentimes you're faced with this kind of a search space. You have a circumstance, and then you have decisions that you make out of that circumstance. You saw the same kind of thing in 291 when you did decision trees. So the same kind of idea. Of course, your decision trees are very small, but imagine a decision trees that might go thousands of levels deep, and you're getting into a real AI kind of problem. So in a situation like that, this kind of depth-first search just to try to find the right solution is not going to work. And so AI often makes the use of heuristics. And rather than a depth-first search, they might do something called a best-first search, which is kind of like breadth-first, which I was talking about before. You first look at these two nodes at this level, and then you go to the next level. But how do you decide which node? Well, there's some kind of a metric that would be done to decide which node is the best node. So there's an evaluation kind of going on, a kind of a heuristic. And that heuristic might need you to kind of search a little bit further down in order to be able to come up with a evaluation of which is the best path to take. But those are the kinds of things that will be happening in AI problems. So AI problems oftentimes are exactly that, a tree, often a really, really huge tree, and navigating through that tree is an issue with AI. Now, for us, doing a depth-first search is going to be fine because the bill of materials is a small hierarchy, so we're going to just content ourselves with that. But I just wanted to introduce you this notion of how a tree complicates things in computer science in much the same way that other self-referential things, and remember, recursion is self-referential, can complicate things in computer science. Okay, so back to the NoSQL slides, and we're going to be focusing, our exercise now is going to be focusing on basically on these last 4 or 5 slides of the PowerPoint. So, and what I'm going to start off by doing is create a new script. So I'm going to get into idle, my Python shell, and I'm going to make a new script. And I'm going to be importing Boto3. Import Boto3 because we're going to be working with the, I didn't want to make that a comment. I will make a comment though. I'll call this produce BOM hierarchy. Okay. And I'll even call it that name. So let me save a file, put it in my temp folder, and I'll call it produce BOM tree, whatever. Okay. And I'm importing Boto3, and I also have to, I'm going to be using the querying stuff, so I'm going to have to import the ATTR from the Boto3 conditions. So this is from slide 29. I'll copy that. I don't need the key, but I do need the ATTR, the attribute class. And I'll go ahead and do my thing with my resources and whatnot. So resource equal Boto3.resource DynamoDB. Did I do that right? Let me run it just to make sure. looks like it, and table equal resource dot table, my AdventureWorks table, AW product BOM, and I should now be able to do a query. Oh, I guess I'm just going to ask the user to enter a product ID, and I'll do a query on that product ID, and I'll see what the result is going to be. So let me just do this. I'll make a variable called product ID equals, and then I'll input from the user their response. So enter product ID, and then they'll enter the product ID. And then I'll do that scan operation. Let me copy that from here and kind of tweak it. So here we are on slide 29. So here's our response equals table.scan. You remember doing that. We did that in a previous exercise. And I guess what I'll do is I'll just say, I'll just copy this, both of these two things. Maybe I'll even copy the comment. Might as well get the specific product. And I'm going to, however, what I want is for the product ID to be equal to the value that the user entered. So I don't want the attribute subcategory, I want the attribute product ID. And I don't want it to be equal to mountain bikes, I want it to be equal to that variable, prod ID. And then if I've done this right, then I should be getting back only a single item because the product ID would have been unique, right? Go ahead and run it. So I'll enter a product ID, I'll make it 950 and see what it gives me. Okay, so let's take a look at what is in items. And there's items, product 950, it's a crankset, it's a component, okay. And it shows me my bill of materials and everything like that. And there's only one of them. It's an array, it gave me an array because the scanner is giving me an array, but there's only one item in it. So I'm just going to say, we're only going to get one item. So I'm going to make a variable called item equal items 0. And now I've got my item that I wanted from doing my query. So I did my query and it gave me what I wanted. Maybe I'll print some stuff about that. So let me just do a print, and I'll call it item, and I'll get product name, and maybe also item category, so I know what this is. I'm going to do it one more time. $9.75 this time. Okay, it's the road 350 W yellow, and it's number 44, and it's a bike. So there you have it. So now that we've done that, now it's time to traverse through the bill of material, and we're going to do this. I'm just going to copy and paste code here, which was the code that was in here. Here's a recursive call. I'm just going to go ahead and copy and paste this. This is going to be the function recurse BOM, and we'll take a look and see what it's doing. It's this should remind you a little bit of that last function that I showed you. The recursion demo function is kind of the same idea, and I'll step to that, show you. And let me put it into the, is it this one? This BOM tree. So here is my function. I have to actually declare it before I use it, so I'll just go ahead and declare it after my import. And you'll notice what it's doing. There's a loop, and it's looping through the BOM. The one problem is if there is no BOM, because remember some products didn't have one, I would be getting an exception. And so I'm handling this key error with the exception. We encountered that before as well. So if there's no BOM, we're stopping. That's our stopping condition. In order to continue, there has to be a BOM below it. So once you get to that lowest level in the hierarchy, it's not going to have a bill of material. We already saw that. I'm doing a little loop here to kind of indent to the appropriate level here, just printing tab, 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 tab to indent. I did something similar with in the previous example, the recurse demo example, because I was putting little asterisks out for indentation. And then I'm printing the name. And here's where I make my recursive call. So we're going to have a loop, and each time the branch out of each node of this tree is going to be however many items there are in the bill of materials array or list. So remember, there's a bill of materials list. Let me go back to this, and we saw here we have our bill of materials list. So however many items there are in that list is how many branches we're going to have off of the tree. So we're basically building a tree. So let's go ahead and call it. So I'm going to call it, and so what is it taking, by the way, as an argument? It's taking the ID, the product ID. It's taking the bill of materials attribute, and it's taking the level number in the tree, and I'm only using the level number really to decide how many tabs I want to go. That's really the purpose of that. So let's take a look and see what happens. So I'm going to go ahead and start the recursion. I'll put a comment here, start recursion. And so I've already got the product, it's got its bill of materials, and I'm going to go ahead and call the function recurse BOM, and I'm passing the product ID, which was what the user had entered right here, and I'm passing the bill of materials attribute, item BOM of the item that was returned, that was given to me from the, and then I have the level, which the level will start at 1. And you'll notice that the level, each time I call in the recursion, is increasing. So let's see if I did this right. Let's see what happens. And what it should do is it should be printing out all of the components, kind of the hierarchy of the components. So let's see if I did this right. I'm gonna run it. Let's give it the 950 and see what it gives me. And voila, there's my bill of materials. Let's try it again and give it the 975 and see what it gives me. So this is a bike, so it has a much deeper bill of materials. The other thing was just a component. And look at all that. It's giving me all of that. That is the bill of materials that came as a result of what was a depth first navigation in this tree. And you can see the tree of the calls. Every time there was a call, something got printed out. So here was, this was the, let me see what happened here. Yeah. So this was the first component, second component, third component, fourth component of the bike. But each of those components had subcomponents. And here we even had a component that had a subcomponent that had a subcomponent under that. So that's your hierarchy. And that's what recursion can do for you with a hierarchy. Okay, now in order to add icing on the cake, we'll do what's needed for that visualization that I was showing you, this pretty little kind of interactive tree visualization. As I said, this is a D3 visualization. D3 is built on top of something called scalable vector graphics, and I'm not going to have time to talk about that in this lecture, but I think I will talk about it in future lectures. And if you'll recall, in Story Analyzer dashboards, you have a lot of D3 visualizations. The word clouds are D3 visualizations. The chord is D3. The force graph is a D3. The timeline is a D3. So you have a lot of D3 visualizations in those dashboards. And this is another kind of a D3 visualization, this tree visualization. And in general, when you are creating visualizations, and this was also true when you created your Google visualizations, those visualizations have an expected data format coming to them. So there was an expected data format for the pie, and there was an expected data format for the what did we do? Did we do bar charts? I don't remember exactly what we did, but there were expected data formats for each of those visualizations. The same was true in Tableau. Each visualization has an expected data format. So, and of course, it's the same as true here. And so there's an expected data format for these visualizations as well. So let's take a look at the underlying files. I'm going to take this HTML file, and I'm going to download it, put it into my temp file. So let me just go ahead and save it into my temp folder. Okay, I'm going to save this, and I'm going to open it up. And oh, by the way, I'm also going to need to, if I'm going to be actually using it, let me go to the modules again. So that's the HTML file, and that HTML file is making use of a JavaScript file here called treed3.js, so I'm going to download that as well. I'm going to save that as well into my temp folder. And now if I go in my temp folder, and if I go ahead and double click on that, I'll see that very same thing that we saw in Canvas. So let's take a look at what the HTML file has in it. And it's actually a very sparse little HTML file. And it has, all right, let's look at the scripts here. There's a script here that is, you could actually follow that link and you'll see the code. This is open source. This is D3's library. And it is the source of the code that you'll see has been minimized. That's why it's v4.min. But it's open source. D3 is all open source. And you'll also notice that there is another script where I'm referencing that tree D3 JavaScript. And I might as well pull it up and show it to you. I'm not going to delve into details about this, and I'm not requiring you to code D3 code, but this is making use of a bunch of D3 libraries, and it's making use of the tree in particular visualization. It's making use of the D3 libraries. But the thing that is of interest to us here is the data that we're giving it. I have a variable here called tree data, and what am I giving it? I'm giving it JSON. Let me go ahead and copy that. And I'm going to put it into JSON pretty print so you can see what it looks like pretty printed. And it'll look very similar. It's basically, it's just the bill of materials. Well, it's the yeah, it's wait a second. Yes, it is It is that one bike and its bill of materials in the hierarchy. So that's what this JSON has given us, that hierarchy. However, notice what it's really giving us is not exactly the same data as if you were just getting the JSON of the AdventureWorks data warehouse. There's nothing like name and children, for example, that are coming down from the DynamoDB. We generate this. We are going to generate a dictionary that has name and children properties to them in order to make it consistent with what the expectations of that visualization is. So again, we go to here, and if we look at what item looks like, I'm going to go ahead and copy that. Oh, I'm going to have to do a JSON dumps. Well, let me just look at it. If I look at what item looks like, I'll just view it. We got product ID, we got subcategory, we got list price. Those are the attributes that we're dealing with. We got to convert that into a dictionary that's going to be a dictionary that will consist of a name property and a children property, and that children property is going to be a list, and it will in turn consist of names and children's, and so that's the hierarchy that we're going to be creating, and we'll use the recursion to do that. So let's go back to the PowerPoint. And so here's the code here that we're going to be doing. There's a couple of things. We're going to be adding some code into our function, into our recursive function. We're going to be adding a new argument in our call to the recursive function. We're going to be making, in our main part of the script, a variable, we'll call it tree, and it's going to have a name, and it's going to have an empty array for children, and then we're going to modify our call to include that as the argument. So let's start by copying this code right here, which is going to be creating a node every time we go into the function. We're going to be creating a new tree node. Let me go to is that this one? Yeah. So we're putting it right before the try block. So in addition to printing out our component, we're also making a new tree node. And what does that tree node has? It has a name, which is going to be the component name, which was what we printed out, and it has an empty list for children. And then we're going to append it to the children of what came in. Well, in order to have something came in, I have to put in a new attribute, a new argument, and I'll call it tree. So tree is this gradually building tree. It's a dictionary which is made up of a string and a list, and that list would be a list of dictionaries which are made up of strings and lists, etc. So let's go back to the PowerPoint. So I have changed my my declaration of this function so that now it includes, tree as an argument. So I think I've done everything I need to do within the function. Now, in order to prepare to call the function, I need to one other thing I had to do is in my recursive call to the function, in addition to having the component ID and the bill of materials and adding one to the level, now I have to have this new tree node right here that I just created is going to be passed as an argument. Oops. Yeah. Oops. Tree node is going to be passed as an argument here. So now I think I've done everything I need to do in my function. So what did I do? I'm taking in an argument, I'm creating a node, I'm appending it to the tree that I've taken it in. So it becomes a node within that tree, within the children of that particular tree node. And then I've also passed it as an argument to my recursive call. And so now in the main part of my code, when I'm about to make the call here, what do I need to do? I need to create the tree in the first place that would be called, which would be the product that the user had asked for. And it's going to also have empty children. And then I'm going to change my recursive call because I'm going to have to pass that as the argument. So let me just copy this code right here. And I'm going to replace where it says start recursion. I'm going to replace that. And if I've done it right, then I should be generating the data that will ultimately be in this variable called tree. And that data I can use and put into my HTML file here. So ultimately what I want to do is I want to replace this particular touring bike blue with something else that I've generated. Let me see if I can do that. I think I'll kill this shell right here and I'll run it again. Oops, I got a syntax error. Why? What happened here? Invalid syntax. Oh, I forgot a comma. Of course. All right, let's try it again. So let's try this 975. This okay, looks like it's done what it needed to do. Let's take a look at what tree looks like. So tree is now a dictionary, as we can see. It's got name and children. That's exactly what we wanted. We wanted a dictionary, but I can't put a dictionary into JSON. I have to convert it to JSON. So I'm going to, had I already imported JSON? I did not. So I'm going to import JSON in my shell. And I'm going to call the JSON.dumps dump_s function. So what does dump_s do? It takes as an argument, it takes a dictionary or perhaps a list. It takes Python data structure, dictionary and list, and it generates the corresponding JSON string. So it's generating a string. And that string is going to be what I'm going to need to pass, what I'm going to need to replace all this data with. So I'm going to say JSON dumps and tree. And there it is. And you can see it generated a string because it's within single quotes, right? Here's a single quote at the beginning, and then down at the very end is another single quote. So I want to take what's between those quotes. I'm going to copy that. And I'm going to go into my HTML file, and I'm going to paste it. I just replace all that stuff with this. And now, what I should find, if I run this, is no longer the blue bike, but the yellow bike. And let's see if it did what I think it's going to do. And there you have it. the yellow bike, with its bill of materials and all the rest. So basically that's it for our exercises for NoSQL. So what I'm going to be looking for in related to this particular exercise, this particular video, is the script, the code that we just built together. And also I'd like you to pick a product, just something different from what I showed you, something different from what's in there originally, and replace your HTML with that product, and that'll be part of your deliverables as well. And then after this, the next technical foray that we take is going to be into AI and machine learning, and we'll be doing more Python with that as well.